At the beginning of the 20th century, astronomers believed they were already mapping the entire universe. They were not guessing. They were measuring distances, cataloguing stars and tracing clouds of gas and dust with increasing precision. By all available evidence, everything that existed was contained within a single vast structure, the Milky Way. Welcome to Astro Horizons. Here we explore the universe beyond headlines and speculation, focusing on what the science actually tells us about space-time and our place among the galaxies. Then, without warning, the scale of reality broke. Objects once assumed to be nearby were suddenly revealed to be impossibly distant. Distances multiplied not by small factors but by orders of magnitude. Structures thought to be minor features turned out to be entire stellar systems, each containing billions of stars. The universe did not grow slowly. It expanded violently in the human mind. In a single generation, what had seemed like the whole of existence was reduced to a local neighborhood. The Milky Way was no longer the universe. It was merely one example, one data point among countless others. This realization did not emerge from philosophy or speculation. It came from measurements, from light curves, from careful observations that left no room for interpretation. The evidence was unavoidable. There were other galaxies, not theoretical ones, not distant possibilities, but real massive systems scattered far beyond anything humans could ever reach. This series begins at that moment, the moment we stopped asking what the universe looks like, and started asking how many worlds like ours exist beyond it. Before we explore strange structures, extreme environments, or the question of life beyond the Milky Way, we must understand the first step that made all of those questions possible, the step beyond home. For centuries, the Milky Way was not understood as one structure among many. It was understood as the structure. Everything visible in the sky appeared to belong to a single system, and there was no observational reason to think otherwise. Early telescopes reinforced this belief rather than challenging it. When astronomers pointed their instruments toward the faint haze of the Milky Way, they did not see a boundary. They saw continuity. Stars blended into denser regions. Bright points faded into unresolved light. The sky appeared layered, not segmented. Crucially, distance was the missing variable. Without reliable methods to measure how far stars truly were, brightness became the default proxy. A dim object was assumed to be nearby and small. A bright one was assumed to be distant and large. This assumption worked reasonably well within the local stellar neighborhood, but it collapsed beyond it. Within this framework, faint spiral-shaped smudges were easy to misinterpret. They were catalogued as nebulae, clouds of gas and dust forming stars somewhere inside the Milky Way. Some appeared round and featureless. Others showed hints of structure, even delicate spiral patterns. But structure alone did not imply scale. A small object nearby could look just as complex as a vast object far away. Nothing about these observations demanded a larger universe. Even the most detailed star maps of the time showed the Milky Way as enormous. It spanned the entire sky. Its thickness varied with direction. Its densest regions aligned along a single plane. To the astronomers of the 19th century, this looked exactly like what a universe should look like. A vast system of stars with clouds and clusters embedded throughout. The idea that similar systems might exist far beyond it raised a serious problem. If those faint nebulae were truly distant, then their intrinsic brightness would have to be extraordinary. Their size would be immense, and their separation from us would stretch far beyond any scale science had yet confirmed. Such conclusions felt unnecessary, and unnecessary conclusions are rarely embraced in science. Instead, the Milky Way was treated as the full cosmic environment. Models of stellar motion, star formation, and galactic structure were all built under that assumption. Astronomers debated the size and shape of the Milky Way itself, but not its exclusivity. The universe was large, complex, and mysterious, but singular. This was not a failure of imagination. It was a consequence of evidence. Without a clear way to measure extreme distances, the sky offered no obvious warning that the universe extended far beyond our galactic borders. The Milky Way appeared self-contained. Its stars obeyed coherent patterns. Its dust lanes and clusters followed recognizable distributions. Everything seemed to belong to one connected system. Only later would scientists realize how deceptive that coherence was. What appeared unified was merely local. What appeared complete was only nearby. And what appeared to be the universe was in reality just the first structure humans happened to be born inside. Before other galaxies could be discovered, the Milky Way first had to stop being mistaken for everything. Understanding the universe does not begin with discovering new objects. It begins with learning how far away the objects you already see actually are. For early astronomers, distance was not just difficult to measure, it was fundamentally ambiguous. The sky offered no depth cues. Stars did not grow larger as they approached or smaller as they receded. They remained fixed points of light scattered across a flat backdrop. Brightness became the only available clue. A brighter star was assumed to be closer. A dimmer one was assumed to be farther away. Within the immediate stellar neighborhood, this approximation worked well enough. But beyond it, brightness stopped correlating reliably with distance. Intrinsic luminosity varied wildly from one star to another. Two stars could appear identical in the sky while differing enormously in size and power. One could be a small nearby star. The other could be a massive distant giant. Without an independent measure of distance, there was no way to tell which was which. This limitation shaped everything astronomers believed about the Milky Way. When spiral nebulae appeared faint, they were interpreted as nearby clouds. When they appeared structured, they were assumed to be modest in scale. Nothing in their appearance forced astronomers to imagine distances far beyond the known limits of the galaxy. Even parallax, the most direct method for measuring stellar distance, quickly reached its limits. Beyond a few thousand light years, the apparent motion of stars against the background became too small to detect. The Milky Way, however, was already believed to span tens of thousands of light years. Everything beyond that remained effectively unmeasurable. This created a subtle illusion. If distances could not be measured, they could not challenge existing models. And if they could not challenge those models, the Milky Way remained unthreatened as the universe itself. As telescopes grew more powerful, they revealed greater complexity, not greater scale. More stars, more nebulae, more detail, but not more depth. The universe appeared richer, not larger. Light unknowingly was the source of the deception, because light does not reveal distance directly. It carries information but not context. It arrives stripped of scale. A billion-year journey leaves no mark on a photon that announces how far it has travelled. To turn light into distance, astronomers needed something new, a cosmic ruler, a reliable standard that could be used to measure vast separations with confidence. Until that tool existed, the universe remained compressed, not in reality but in human understanding. And as long as distance stayed ambiguous, the idea of other galaxies remained unnecessary. That changed when astronomers learned how to read time itself from starlight. Only then did the sky begin to unfold in depth. The breakthrough did not come from building larger telescopes. It came from recognizing a pattern hidden inside starlight. In the early 20th century, astronomers studying variable stars noticed something unusual. Certain stars did not shine at a constant brightness. Instead, they pulsed rhythmically, growing brighter and dimmer over precise repeatable intervals. These were Cepheid variables. At first, their behavior seemed like a curiosity, but careful observation revealed a crucial relationship. The period of a Cepheid's pulsation was directly linked to its intrinsic brightness. The longer the cycle, the more luminous the star truly was. This discovery transformed Cepheids into cosmic measuring tools. By comparing how bright a Cepheid appeared to how bright it had to be, astronomers could calculate its distance. For the first time, light carried not just information but scale. When Edwin Hubble applied this method to stars inside the spiral nebulae, the results were staggering. Cepheid variables were found embedded within the Andromeda Nebula. Their calculated distances placed them far beyond the outer limits of the Milky Way, not near its edge, not just outside its halo, but separated by distances so vast that no known model of the galaxy could contain them. The implication was unavoidable. Andromeda was not a nebula inside the Milky Way. It was an entire galaxy of its own. This was not a gradual realization. It was an abrupt rupture. Overnight, the universe multiplied in size. The Milky Way lost its monopoly on existence. What had been considered peripheral detail became central truth. If Andromeda was a galaxy, then the countless other spiral nebulae scattered across the sky were likely the same. Each one a massive system of stars, gas dust, and dark matter. Each one independent, each one distant beyond any physical reach. Astronomy crossed a threshold. Before this moment, the universe had one structure. After it, the universe had many. The consequences reached far beyond classification. Models of cosmic structure had to be rebuilt. The scale of space itself had to be reimagined. Even humanity's position in the cosmos shifted permanently. We were no longer inhabitants of the universe's central system. We were residents of one galaxy among others. The discovery did not provoke celebration. It provoked recalibration. Scientific humility replaced cosmic certainty. The universe had revealed that it was far larger and far less centered on us than anyone had assumed. From this point forward, other galaxies were no longer a theoretical idea. They were an observed fact. And once that fact was established, the sky could never look the same again. Once the existence of other galaxies was accepted, a deeper question immediately followed. What exactly is a galaxy? At first glance, the answer seemed obvious. A galaxy was simply a large collection of stars similar to the Milky Way existing somewhere else in space. Early descriptions leaned heavily on familiarity. Other galaxies were imagined as distant copies of our own, scattered across a larger cosmic background. But this assumption did not survive closer scrutiny. As observations improved, it became clear that the Milky Way was not a universal template. Other galaxies differed in size, shape, structure, and behavior in ways that could not be explained by small variations. Some were tightly packed and smooth, lacking any obvious spiral structure. Others were distorted, fragmented, or asymmetrical, showing no clear center at all. More importantly, galaxies were not static objects. Each one carried its own history. Its stars formed at different times, at different rates, under different conditions. Some galaxies burned through their gas, rapidly creating stars in intense bursts before fading into relative quiet. Others formed stars slowly and steadily over billions of years. A galaxy's appearance was not just a snapshot of its structure, but a record of its past. This forced a conceptual shift. Other galaxies were not merely locations elsewhere in space. They were independent systems with distinct physical environments. Each galaxy shaped how stars formed within it. Each controlled the radiation field's gravitational forces and chemical evolution of its contents. Even the long-term stability of planetary systems depended in part on the type of galaxy they inhabited. In this sense, a galaxy functioned less like a backdrop and more like an ecosystem. Two galaxies of similar size could produce radically different outcomes for the stars inside them. One might host frequent supernova explosions and intense radiation near its core. Another might remain relatively calm for billions of years. These differences mattered even if they were invisible at first glance. Recognizing this complexity changed the role of galaxies in astronomy. They were no longer just markers used to map the universe's large-scale structure. They became laboratories. Each galaxy offered a different combination of initial conditions, allowing scientists to test how matter behaves under varying cosmic environments. The phrase "other galaxies" began to carry real weight. It no longer meant faraway versions of home. It meant alternative cosmic histories unfolding beyond our reach. And this realization quietly set the stage for a much larger question. If galaxies themselves differ so dramatically, then how typical is the Milky Way? That question would soon prove impossible to ignore. Humanity has never traveled beyond the Milky Way. Not physically, not even close. The distances involved are so extreme that even the nearest major galaxy lies far beyond any realistic trajectory. At the speeds achieved by current spacecraft, reaching Andromeda would require tens of billions of years longer than the age of the universe itself. And yet in another sense, we have already left home. Telescopes allow us to observe other galaxies as they were millions or even billions of years ago. Light crosses the intergalactic void, carrying information about stars that no longer exist, about structures that may have changed beyond recognition by the time their photons arrive. Observation replaces travel. This creates a strange asymmetry in our relationship with the universe. We can study places we will never reach. We can analyze systems we will never influence. Other galaxies become known but forever untouchable. The space between galaxies reinforces this separation. Intergalactic space is not simply empty. It contains thin streams of gas-faint radiation and the gravitational influence of dark matter. But compared to the dense interiors of galaxies, it is a realm of extreme isolation. Matter is spread so thin that interactions become rare. Star formation nearly ceases. Galaxies are islands of activity embedded in a vast quiet medium. From within the Milky Way, this isolation is invisible. The night sky does not show the emptiness between galaxies. It compresses depth into a single surface. Only through measurement and inference does the true separation become clear. This isolation has consequences. Galaxies evolve largely on their own. They carry their internal dynamics shaped by their mass composition and history. Interactions occur, but they are infrequent, and often violent collisions merge as tidal distortions that reshape entire systems. For most of cosmic history, galaxies live in solitude. Understanding this solitude is essential. It explains why galaxies can differ so radically from one another. It explains why local conditions matter so much. And it explains why leaving the Milky Way is not merely a question of propulsion, but of fundamental cosmic scale. We are residents of a gravitationally bound system, surrounded by distances that resist traversal. Leaving home in the cosmic sense does not involve movement. It involves perspective. By observing other galaxies, we step outside our local environment intellectually, even as we remain physically confined within it. And as that perspective widens, the universe begins to reveal just how crowded and how distant it truly is. Once distance could be measured reliably, the universe began to behave in a way that defied intuition. Early galaxy counts did not suggest a gentle expansion of scale. They suggested an explosion. Each improvement in telescope sensitivity revealed not just a few additional galaxies, but thousands, then tens of thousands, then more than anyone had expected to find. Deep observations turned what appeared to be empty regions of sky into dense fields of light. Areas once assumed to be nearly blank were shown to contain vast populations of galaxies layered behind one another across enormous stretches of space. The implication was unsettling. If a small patch of sky could contain thousands of galaxies, then the total number across the observable universe had to be staggering. Not millions, not billions, but numbers so large they resisted meaningful comparison. Estimates climbed steadily as observations improved, eventually reaching into the trillions. This was not a matter of counting errors. It was a consequence of depth. Every increase in observational reach extended the universe not just outward but backward in time. Light arriving from distant galaxies had been traveling for billions of years. Each faint point represented a system seen in an earlier stage of cosmic history. The universe was not a static collection of objects. It was a layered record of evolution. This realization introduced a cognitive problem. Human perception evolved to navigate environments measured in meters and kilometers, not in millions of light years. Our intuition expects emptiness to dominate. But on cosmic scales, structure persists across vast distances. Galaxies are not evenly distributed, yet they are not rare. They trace filaments, clusters, and superclusters, forming patterns that stretch across hundreds of millions of light years. What looks sparse locally becomes dense when viewed across sufficient scale. The shock was not simply numerical, it was conceptual. The Milky Way, once assumed to be the central framework of existence, was now one small node in a network of unimaginable size. Its importance diminished not because it changed, but because everything else was finally revealed. Importantly, this scale was not optional. It could not be ignored or simplified. Models of cosmic evolution had to accommodate it. Theories of structure formation had to explain how so many galaxies could emerge, organize, and persist over cosmic time. The universe had crossed a threshold where familiar language struggled to remain useful. When numbers reach into the trillions, they stop behaving like quantities and start behaving like abstractions. And yet every one of those abstractions corresponds to a real galaxy, governed by real physics containing real stars. The scale shock did not end with acceptance. It reshaped the questions astronomers asked. Once the universe was known to contain vast numbers of galaxies, the focus shifted from existence to distribution, from detection to comparison, from isolation to context. And with that shift came a quieter, more unsettling thought. If galaxies are this numerous, then the Milky Way may not be special at all. It may simply be typical, or worse, it may be an exception. As the number of known galaxies grew, a subtle but profound question began to surface. Not about how many galaxies exist, but about what kind of galaxy we inhabit. The Milky Way had long served as the unspoken reference point for understanding galactic structure. Spiral arms, steady star formation, a relatively calm central region, and a long-lived population of stars formed the baseline against which theories were built. But once astronomers began comparing it to large samples of other galaxies, that baseline started to look less stable. Spiral galaxies, it turned out, were not the dominant form. Many galaxies lacked clear spiral structure altogether. Elliptical galaxies, massive and smooth, contained mostly old stars and little active star formation. Irregular galaxies showed no obvious symmetry shaped by past interactions or ongoing disruption. The Milky Way's orderly disk was not universal. Even among spiral galaxies, significant differences emerged. Some formed stars far more rapidly, flooding their interiors with radiation and supernovae. Others had largely exhausted their gas billions of years ago. Some possessed active central black holes that dominated their energy output. Others remained comparatively quiet. The conditions inside galaxies varied widely even when their shapes appeared similar. This raised an uncomfortable possibility. If the Milky Way occupies a narrow region of galactic parameter space, then many of the assumptions drawn from it may not generalize. Star formation histories, chemical enrichment, and long-term stability might follow very different paths elsewhere. In other words, what we experience as normal may be uncommon. This question extended beyond morphology. The Milky Way's environment mattered as well. It resides in a relatively small group of galaxies, avoiding the dense cores of massive clusters where gravitational interactions are frequent and disruptive. Its star formation rate is moderate. Its central black hole is massive but not aggressively active. These factors may not be accidental. Some astronomers began to ask whether the Milky Way's apparent calm was the result of rare circumstances, a specific mass range, a specific merger history, a specific cosmic neighborhood. Taken together, these conditions may have produced an unusually stable galactic environment over billions of years, or they may be entirely typical. At this stage, the data did not offer a definitive answer. What it did offer was perspective. The Milky Way could no longer be treated as the default example of how galaxies behave. It was one data point among many embedded within a distribution that spanned enormous ranges of scale and activity. This realization carried a quiet consequence. If galaxies differ this dramatically, then understanding the universe requires more than studying our own. It requires comparison, classification, context, patterns drawn from diversity rather than familiarity, and once comparison begins, another shift becomes inevitable. If the Milky Way is not representative, then the universe beyond it may operate under conditions we've barely begun to imagine. That realization does not conclude the story of other galaxies. It opens it, and in the next step beyond home, we confront the fact that most galaxies do not resemble the one we know at all. The discovery of other galaxies did not answer humanity's deepest questions about the universe. It made those questions unavoidable. Before this realization, the Milky Way provided a sense of completeness. Even in its mystery, it felt self-contained, a single structure governed by a single set of rules. Once other galaxies entered the picture, that simplicity vanished. The universe was no longer something that could be understood by studying one example in isolation. Every galaxy carried its own conditions, its own past, its own balance between order and chaos. The Milky Way became a local case study rather than a universal model, and with that shift, astronomy moved from certainty to comparison. This first step beyond home was not about exotic phenomena or extreme environments. It was about scale, context, and humility, about realizing that what feels central is often merely local, and what feels complete is often only the beginning. Other galaxies did not redefine the universe by being strange. They redefined it by being numerous. Once that truth was accepted, there was no return to a smaller cosmos. The universe could no longer be imagined as a single system with distant decorations. It became a population, a vast collection of independent worlds shaped by different histories and governed by the same underlying laws. This understanding reshaped every branch of modern astronomy. It altered how we think about structure, evolution, and time itself, and it quietly reframed one of the most important questions we can ask. Not where we are in the universe, but how typical our place really is. Part 1 ends here, not with an answer, but with a boundary crossed. The boundary between a universe centered on home, and a universe defined by diversity. Because once we step beyond the Milky Way, the next realization comes quickly. Most galaxies do not resemble it at all, and that is where the journey truly begins. Once astronomers accepted that other galaxies existed, a quiet assumption followed almost immediately. They assumed those galaxies were like ours, not identical in every detail, but similar in spirit. Flat disks, graceful spiral arms, a steady rhythm of star formation, a long-lived balance between order and motion. The Milky Way became the unspoken template, a reference against which all other galaxies were measured. This assumption felt reasonable. It was based on the only galaxy humans could study from the inside. Familiarity filled the gaps where data was missing. But familiarity can be misleading. As surveys expanded and observations sharpened, a pattern began to emerge that did not fit the template. Many galaxies lacked spiral arms entirely. Others showed no clear structure at all. Some were smooth and silent, filled with ancient stars and little activity. Others were distorted, unstable, or violently reshaped by their environments. The Milky Way was not appearing at the center of this diversity. It was appearing off to the side. This realization did not arrive as a single discovery. It surfaced gradually through comparison rather than surprise. The more galaxies astronomers observed, the harder it became to argue that our home represented a standard case. The uncomfortable possibility began to take shape. What if the Milky Way is not typical? What if it is unusually calm, unusually ordered, unusually stable? If that is true, then many of our intuitions about galaxies are built on an exception rather than a rule. And if our galaxy is an outlier, then understanding the universe requires letting go of the idea that normal exists at all. In this part of the journey, we step fully outside our local bias. We stop using the Milky Way as a reference, and we confront a universe filled with galaxies that do not resemble home in any meaningful way. Because once comparison replaces familiarity, a deeper truth becomes impossible to ignore. Most galaxies are nothing like the one we know. The assumption that other galaxies resembled the Milky Way did not emerge from arrogance. It emerged from necessity. For most of the 20th century, the Milky Way was the only galaxy available for detailed study. Astronomers could measure the motions of its stars, map its gas clouds, and trace its spiral structure from within. No other galaxy offered comparable resolution. Everything else appeared distant, faint, and compressed into a handful of pixels. When information is scarce, analogy becomes a tool. If one system is well understood and others appear similar at a distance, it is natural to treat the known case as representative. Early images of nearby galaxies reinforced this approach. Spiral patterns were among the easiest features to recognize even with limited resolution. Bright cores and sweeping arms stood out clearly against the background. Elliptical and irregular galaxies by contrast were harder to interpret. Without fine detail, their smooth or chaotic appearances could be mistaken for observational limitations rather than intrinsic differences. A lack of visible structure was often attributed to poor resolution, not to a fundamentally different galactic form. This introduced a subtle bias. Galaxies that looked like the Milky Way were classified as normal. Galaxies that did not were treated as special cases. The language itself reflected this mindset. Terms like regular and irregular did not describe how common a galaxy type was. They described how closely it matched expectations shaped by our home galaxy. The Milky Way quietly became the benchmark, not because it was proven typical, but because it was familiar. Classification systems amplified this effect. Early galactic taxonomies organized galaxies along sequences that implied evolutionary progression, often placing spiral galaxies near the center of attention. Ellipticals were framed as end states. Irregulars were framed as incomplete or disturbed versions of a more orderly form. In reality, these categories described appearance, not destiny. The bias persisted because it was rarely challenged. Surveys were limited in scope. Samples were small. Many galaxies were too faint or too distant to resolve clearly. Within these constraints, the Milky Way remained a convenient anchor point. Even theoretical models leaned on this assumption. Simulations of galaxy formation were often tuned to reproduce Milky Way-like properties, because those properties were the best constrained. Success was measured by similarity to home, reinforcing the idea that home represented the norm. Only later would astronomers recognize the circular nature of this reasoning. By assuming the Milky Way was typical, they built tools that preferentially identified galaxies like it. By identifying galaxies like it, they reinforced the assumption that it was typical. Breaking this loop required something new, not a better model of the Milky Way, but a broader view of the universe beyond it. That broader view would soon reveal just how narrow our original assumptions had been. The first serious challenge to the Milky Way as universal template came not from chaotic systems, but from galaxies that appeared almost too simple. Elliptical galaxies lacked the features astronomers had come to associate with galactic structure. There were no spiral arms, no thin disks, no obvious regions of active star formation. Instead, these galaxies appeared smooth and rounded, their light distributed evenly outward from a central concentration. At first, this simplicity was puzzling. If spiral structure represented a mature organized state, then ellipticals seemed incomplete, or worse, degraded. Early interpretations often framed them as systems that had somehow failed to develop properly, or had exhausted their potential. Closer study overturned this view. Elliptical galaxies were not small or primitive. Many were among the most massive galaxies known. They contained enormous numbers of stars, often exceeding those found in typical spiral galaxies. Their apparent simplicity concealed immense scale. What distinguished ellipticals was not a lack of matter, but a lack of gas. Most of their stars formed early during intense periods of star formation that consumed available gas rapidly. Over time, little material remained to form new stars. What was left was a population dominated by old, long-lived stars moving in randomized orbits rather than organized rotation. This led to a fundamentally different internal environment. Without ongoing star formation, elliptical galaxies grew quieter with time. Supernovae became rare, radiation levels declined, stellar populations aged in place. These galaxies did not evolve through continuous renewal, but through slow fading. Crucially, elliptical galaxies were not rare. They were especially common in dense environments such as galaxy clusters where interactions and mergers were frequent. In these regions, spiral galaxies often collided and merged, their disks disrupted their gas, heated or expelled. The end result was an elliptical galaxy, massive, smooth and largely inert. This had unsettling implications. If ellipticals formed naturally through common processes, then spiral galaxies like the Milky Way were not the inevitable outcome of galactic evolution. They represented one possible pathway among many, not a default state. In some environments, the Milky Way's structure would not survive for long. The discovery of elliptical galaxies forced astronomers to confront a new reality. Galactic order did not always take the form of rotating disks and spiral arms. Stability could exist without structure. Mass could exist without activity. The Milky Way's graceful form, once assumed to be typical, now looked increasingly specific. And ellipticals were only the beginning. Beyond them lay galaxies where even simplicity gave way to disorder. If elliptical galaxies challenged the idea that spiral structure was universal, irregular galaxies challenged the idea that structure was necessary at all. Irregular galaxies do not conform to clean categories. They lack symmetrical shapes. They show no clear spiral arms, no smooth elliptical profiles, and often no obvious center. Their stars and gas are distributed unevenly, forming clumps, filaments, and distorted regions that resist simple description. At first, irregular galaxies were treated as curiosities. Their chaotic appearance made them difficult to classify, and early observations often dismissed them as incomplete or transitional objects. But as surveys expanded, it became clear that irregular galaxies were not rare anomalies. They were a significant fraction of the galactic population, particularly among smaller systems. Their disorder was not accidental. Many irregular galaxies bear the scars of interaction. Gravitational encounters with larger neighbors can stretch and tear their structure, pulling stars and gas into elongated streams. Close passes can trigger bursts of star formation in some regions while stripping material from others. Over time, these interactions erase symmetry. In other cases, irregularity arises from scale. Low-mass galaxies struggle to impose order on themselves. Their gravitational pull is weaker, making it harder to form stable rotating disks. Stellar feedback from supernovae and stellar winds can more easily disrupt gas clouds, preventing long-term organization. The result is a galaxy shaped by local events rather than global patterns. Irregular galaxies often exhibit intense localized star formation. Bright clusters of young stars coexist with vast regions of relative emptiness. Chemical composition varies sharply from one region to another. Evolution proceeds unevenly without the smoothing effect of large-scale structure. This stands in sharp contrast to the Milky Way. Our galaxy's disk enforces coherence. Stars follow ordered orbits. Gas settles into defined lanes. Star formation, while variable, unfolds within a stable framework. Irregular galaxies lack this regulatory mechanism. The existence of these systems reveals an important truth. Order in the universe is not guaranteed. Galaxies do not naturally evolve towards symmetry. They are shaped by their environment, their mass, and their history of interactions. In many cases, chaos is not a temporary phase. It is a long-term condition. For observers living inside such galaxies, the night sky would not reflect the calm regularity familiar to us. Stellar distributions would be uneven. Bright regions would cluster unpredictably. Long-term stability would be uncertain. Irregular galaxies show that the Milky Way's structure is not simply a consequence of physics, it is a consequence of circumstance. And as disruptive as irregular galaxies appear, they still represent only one end of a broader spectrum. Beyond them lie galaxies that are not disordered but silent. After confronting galaxies shaped by chaos and interaction, astronomers encountered a different kind of surprise. Galaxies that appeared almost motionless in time. These systems were not small or insignificant. Many were massive, well-formed, and structurally stable, yet they showed little evidence of ongoing star formation. Their interiors were dominated by old stars, their light reddish and subdued. New stars were no longer being born in meaningful numbers. At first, this quietness seemed counterintuitive. Galaxies were expected to be active. Gas clouds collapse. Stars ignite. Supernovae explode. These processes defined the dynamic image of the universe. But in these galaxies, the cycle had slowed to a near standstill. The explanation lay in fuel. Star formation requires cold gas. Without it, even the largest galaxy becomes inert. In many quiet galaxies, gas had either been consumed early or removed entirely. Powerful episodes of star formation in the past had burned through available material. In dense environments, interactions with surrounding hot gas stripped galaxies of their remaining reserves. What remained was a stellar population frozen in time. These galaxies continued to orbit within clusters, their stars moving along stable paths, but their internal evolution had effectively paused. Chemical enrichment slowed, new planetary systems became rare. The future was defined more by aging than by transformation. This challenged another assumption. If galaxies could reach stable, long-lived states with minimal activity, then dynamism was not a universal trait. Some galaxies did not evolve continuously. They reached equilibrium and stayed there. The Milky Way, by contrast, occupies an unusual middle ground. It has neither exhausted its gas nor consumed it too rapidly. It continues to form stars at a moderate rate, balancing renewal with stability. This balance may not persist indefinitely, but it has lasted long enough to shape a complex internal environment. Quiet galaxies show that this balance is not inevitable. They represent alternative endpoints of galactic evolution shaped by early conditions and environmental influence. Their existence implies that many galaxies spend most of their lives in states far removed from the dynamic image we associate with cosmic activity. For an observer within such a galaxy, the universe would appear calmer, dimmer, and less variable over time. The dramatic events that punctuate the Milky Way's history would be rare or absent. Silence in this context is not emptiness. It is the outcome of processes that have already run their course. And yet for every galaxy that grows quiet, there exists another that does the opposite, one where activity does not fade but intensifies. If quiet galaxies represent evolution slowed to a whisper, other galaxies exist at the opposite extreme. They are defined not by balance but by excess. These are galaxies where star formation does not proceed gently. It erupts. In starburst galaxies, stars are born at rates tens or even hundreds of times higher than in the Milky Way. Vast clouds of gas collapse almost simultaneously, igniting waves of stellar birth that flood entire regions with radiation, shock waves, and intense heat. This violence is not random. Starbursts are often triggered by disruption. Collisions between galaxies compress gas, forcing it inward. Tidal forces tear apart stable structures, funneling material toward dense regions where gravity overwhelms resistance. In some cases, even a close pass without a full merger is enough to destabilize a galaxy's internal balance. Once the process begins, it feeds on itself. Massive young stars burn fiercely and die quickly, exploding as supernovae that inject energy back into their surroundings. This energy can compress nearby gas clouds, triggering further star formation, or it can expel gas entirely, shutting the process down. In starburst galaxies, both effects occur simultaneously, creating environments of extreme instability. The internal conditions inside these galaxies are unlike anything found in the Milky Way. Radiation levels are elevated. Supernova rates are dramatically higher. Magnetic fields are stronger. Gas turbulence dominates over ordered motion. Long-lived stable regions become rare. At the centers of many violent galaxies lies another source of disruption. Supermassive black holes, when actively feeding, can outshine their entire host galaxy. Jets and winds launched from these active galactic nuclei inject enormous amounts of energy into surrounding space. Gas is heated, expelled, or prevented from cooling. Entire galaxies can be reshaped by activity occurring within a region smaller than the solar system. The Milky Way possesses a central black hole, but it is comparatively quiet. Its influence is limited. In violent galaxies, the central engine dominates. This contrast is telling. The Milky Way's moderate star formation rate and relatively calm nucleus place it far from these extremes. It has avoided the runaway processes that define starburst systems, at least for now. That avoidance may be a consequence of its mass, its merger history, or simple chance. Violent galaxies reveal that galactic environments can become hostile to long-term stability. They are efficient at producing stars, but inefficient at preserving the conditions required for sustained order. Their brilliance is intense but temporary. In cosmic terms, they burn fast. These galaxies demonstrate that activity alone does not imply longevity. Extremes can accelerate evolution, pushing systems rapidly toward exhaustion or transformation. The Milky Way's restraint, once taken for granted, begins to look unusual. And as astronomers piece together these extremes, quiet galaxies at one end, violent galaxies at the other, a deeper pattern started to emerge, one that linked form, behavior, and history into a single story. By the time astronomers had catalogued quiet galaxies, violent galaxies, smooth ellipticals, and chaotic irregulars, one conclusion became unavoidable. A galaxy's shape is not a starting point. It is a consequence. Early on, galaxy classification focused on appearance. Spirals, ellipticals, irregulars were treated as categories, as if form itself defined what a galaxy was. But as data accumulated, it became clear that morphology was only a snapshot, an outward expression of a much longer and more complex history. Every galaxy carries the record of how it formed and what it endured. One of the strongest influences is merger history. Galaxies rarely evolve in isolation. Over billions of years, they experience close encounters, minor mergers, and sometimes catastrophic collisions. Each event redistributes stars' gas and dark matter, altering structure in lasting ways. A single major merger can erase a spiral disk entirely. When two comparable galaxies collide, ordered rotation is disrupted. Stars are thrown into randomized orbits. Gas is compressed, heated, or expelled. The remnant often resembles an elliptical galaxy, not because ellipticals are primitive, but because they are survivors of violent pasts. Spiral galaxies, by contrast, tend to have quieter histories. To maintain a thin, rotating disk over billions of years, a galaxy must avoid major disruptions. Minor mergers may occur, but they must be gentle enough not to destroy coherence. This requirement alone places spiral galaxies into a narrower evolutionary pathway. Gas supply plays an equally important role. Galaxies that continue to accrete cold gas can sustain star formation and rebuild structure after disturbances. Those that lose access to gas through early consumption, environmental stripping, or energetic feedback drift toward quiescence. Shape follows fuel. Dark matter halos add another layer of influence. The mass and distribution of dark matter determine how tightly a galaxy is bound and how it responds to external forces. A massive halo can stabilize a disk, absorbing disturbances that would otherwise cause fragmentation. A lighter halo offers less protection, allowing chaos to dominate. Seen this way, no galaxy is arbitrary. Irregular galaxies often reflect shallow gravitational wells and frequent disruption. Ellipticals reflect histories of mergers and early intense star formation. Starburst galaxies reflect transient phases driven by interaction and compression. Quiet galaxies reflect exhaustion and isolation. The Milky Way's shape then tells a specific story. It suggests a history with relatively few major mergers, a steady long-term gas supply, a dark matter halo massive enough to enforce order but not so dominant as to suppress disk formation. These conditions are not guaranteed across the universe. They are contingent. This realization reframes how astronomers interpret galactic diversity. Differences in appearance are not cosmetic. They are diagnostic. Each shape encodes billions of years of evolution, interaction, and chance. To understand galaxies, one must read them as histories written in stars. And once history becomes the focus, another pattern begins to surface. Across the universe, most galaxies do not share the Milky Way's particular story. As galaxy surveys grew larger and more systematic, astronomers began to do something that had not been possible before. They stopped studying galaxies one by one and started studying them statistically. This shift changed everything. When galaxies were viewed as a population rather than as individual curiosities, patterns emerged that no single observation could reveal. Distributions replaced anecdotes, frequencies replaced impressions, and the Milky Way, once an assumed reference, became just another data point. That data point did not sit at the center. Across large samples, galaxies clustered toward extremes. Many were either far more active than the Milky Way or far more quiescent. Many showed signs of past disruption, distorted shapes or merger histories that would have destroyed a thin spiral disk like ours. Others had already shut down star formation, entirely settling into long-term dormancy. The Milky Way occupied a narrow middle ground. It was not the most massive, not the most active, not the most chaotic, but it was unusually balanced. Its star formation rate was moderate. Its structure remained coherent. Its central black hole was massive yet largely inactive. Its environment was neither isolated nor violently crowded. Statistically, this combination was not common. This did not mean the Milky Way was unique, but it did suggest that it was not representative of the average galactic experience. Many galaxies lived lives shaped by instability, scarcity, or excess conditions that the Milky Way had largely avoided. The discomfort came from implication. If most galaxies do not resemble ours, then models based primarily on the Milky Way risk overgeneralization. Processes assumed to be typical may in fact be conditional. The long-term stability we observe locally may depend on a rare alignment of factors, rather than on universal principles. In other words, the Milky Way may be a fortunate outcome, not a default one. This realization did not undermine astronomy. It strengthened it. It forced a shift away from parochial thinking and toward comparative understanding. Galaxies had to be studied in context, not isolation. Diversity became data, and with diversity came a deeper question. If most galaxies differ so radically from the one we inhabit, then what other forms might exist beyond the boundaries of what we already know? The answer would not lie among calm spirals or familiar ellipticals. It would lie at the edges of possibility, in galaxies that push physics to its limits. By the end of this part of the journey, one conclusion stands firm. The Milky Way is not a template. It is a single solution among many shaped by a specific history of mergers, gas supply, environment, and timing. Its graceful structure and long-term stability are not guaranteed outcomes of cosmic evolution. They are contingent results. Other galaxies reveal what happens when conditions change. Some grow quiet and fade early. Some burn violently and exhaust themselves. Some never settle into order at all. Together they show that the universe does not favour balance. It permits it occasionally, but it does not enforce it. This changes how we interpret our place in the cosmos. The environment we call home may be unusually calm, not because the universe is gentle, but because we reside in a rare pocket of stability. That possibility reframes everything from how galaxies evolve to how long complex systems can persist within them. Part 2 does not conclude with an answer. It concludes with a correction. The universe is not organized around what we know. What we know is organized around where we happen to live. And once that correction is made, the next question becomes unavoidable. If galaxies can differ this much in form, behavior, and history, then what happens at the extremes? In the next part, we move beyond diversity and into territory where galaxies break expectations entirely. The most extreme other galaxies in the universe. By the time astronomers realized the Milky Way was not typical, another assumption quietly fell apart. They had believed that despite their differences, galaxies at least followed the same basic rules, that they formed gradually, that they grew at predictable rates. That time imposed limits on size, structure, and complexity. Then the observations stopped cooperating. Galaxies began to appear where they should not exist. Massive systems emerged in the early universe when there had barely been time to assemble them. Others stretched across space with so few stars that they bordered on emptiness yet refused to fall apart. Some were dominated by central engines so powerful that the rest of the galaxy seemed secondary. These were not rare anomalies hiding in obscure corners of the sky. They appeared repeatedly across different surveys at different distances under different conditions. The pattern was impossible to ignore. The problem was not that galaxies behaved strangely. The problem was that our expectations were too narrow. Extremes were not breaking the rules. They were revealing that the rules were incomplete. In these galaxies, growth happened too fast. Density dropped too low. Energy concentrated too intensely. Stability vanished entirely. And yet the systems persisted, governed by the same fundamental laws as everything else in the universe. This forces an uncomfortable question. If galaxies can exist in forms this extreme, then what defines a galaxy at all? Where does the boundary lie between structure and chaos, between formation and failure? In this part of the journey, we move past diversity and into understanding limits. We explore galaxies that sit at the edge of what theory allows, and we discover that the universe does not merely tolerate extremes, it produces them because it is at the extremes that the true flexibility of cosmic structure is revealed. According to standard models of cosmic evolution, galaxies are not supposed to appear fully formed in the early universe. After the Big Bang, matter was distributed almost uniformly. Small density fluctuations grew slowly under gravity, drawing gas into dark matter halos. Stars ignited, structures assembled piece by piece. This process was expected to take time hundreds of millions, then billions of years, yet observations began to tell a different story. When astronomers looked deep enough into space, they were also looking far back in time. Light from the earliest galaxies has been travelling for more than 13 billion years before reaching us. These objects appear as they were when the universe was only a few 100 million years old, and some of them look disturbingly mature. Instead of diffuse clouds just beginning to collapse, telescopes revealed compact galaxies already packed with stars. Their stellar populations were surprisingly rich in heavy elements, implying multiple generations of star formation had already occurred. In cosmic terms, they appeared rushed. The launch of the James Webb Space Telescope sharpened this tension. JWST was designed to observe the faint infrared light from the early universe, penetrating dust and red-shifted wavelengths that previous instruments could not access. Almost immediately it began detecting galaxies that challenged established timelines. Systems with masses comparable to modern galaxies were appearing far earlier than models had predicted. The problem was not subtle. To reach such sizes so quickly, these galaxies would have needed to convert gas into stars with extraordinary efficiency. Star formation would have had to begin earlier, proceed faster, or both. Either way, something was missing from the picture. Several possibilities emerged. Perhaps early star formation was far more efficient than expected. Perhaps dark matter halos collapse faster under conditions unique to the young universe. Perhaps feedback mechanisms, winds, radiation supernovae behaved differently when the first stars ignited, or perhaps the initial assumptions were wrong. If galaxies could assemble rapidly under the right conditions, then gradual growth was not a universal rule. It was one pathway among many. In the dense, energetic environment of the early universe, extremes may have been common rather than exceptional. These early forming galaxies force a reconsideration of cosmic history. They suggest that the universe wasted no time in building structure. That complexity emerged not slowly and cautiously, but aggressively. Gravity, gas, and radiation interacted in ways that compressed evolution into astonishingly short windows. In this context, the Milky Way's long, relatively gentle formation begins to look less like a default scenario and more like a delayed outcome. Galaxies that formed too early reveal that time in the universe is not always a limiting factor. Under the right conditions, cosmic structures can arise with startling speed. And if time does not constrain galaxies as tightly as once believed, then neither might mass. That realization leads directly to the next extreme. If galaxies could form earlier than expected, some also appear to grow far larger than expected far too quickly. In the young universe, time was scarce. There had been little opportunity for repeated cycles of star formation, mergers, and gradual mass accumulation. According to conventional models, early galaxies should have been small, lightweight systems still assembling their stellar content. Yet observations contradicted this expectation. Astronomers began identifying galaxies in the early universe, with stellar masses rivaling those of mature galaxies seen billions of years later. These systems contained enormous numbers of stars packed into compact volumes, despite having existed for only a fraction of cosmic history. The mismatch was not trivial. To build such mass so rapidly, these galaxies would have required extraordinarily efficient conversion of gas into stars. In some cases, nearly all available gas would need to collapse into stars with minimal loss. Feedback processes that normally regulate growth, stellar winds, radiation pressure, supernova explosions, would have had to be weaker delayed or temporarily ineffective. This raised fundamental questions about the role of dark matter. Dark matter helps provide the gravitational scaffolding for galaxies. In the early universe, these halos may have collapsed faster and grown more massive than models initially assumed. Dense environments could have accelerated gas inflow, feeding rapid star formation before feedback mechanisms had time to respond. Alternatively, early galaxies may have experienced short-lived but extreme growth phases, assembling most of their mass in brief bursts before settling into slower evolution. Either way, the implication was the same. Mass was not bound to time in the way astronomers had believed. The relationship between age and size, once treated as a reliable guide to galactic evolution, began to fracture. Young galaxies could be massive, old galaxies could be relatively small. Growth histories varied far more than expected. This variability challenged the idea of a single evolutionary timeline. Instead of a smooth progression from small to large, the universe appeared to support multiple growth pathways. Some galaxies grew gradually, others grew explosively. Some reached maturity early and changed little afterward. Others remained in flux for billions of years. The Milky Way's mass, when viewed through this lens, reflects a moderate and extended growth history rather than a rapid one. It avoided the extreme efficiencies that characterized these early massive galaxies. These systems demonstrate that galactic mass is not merely the outcome of long duration. It can be the result of short, intense episodes shaped by conditions unique to the early cosmos. If galaxies could grow too large too fast, then assumptions about scale itself needed reconsideration. And scale, as it turns out, is not only about how much matter a galaxy contains, but how that matter is distributed. That leads to another extreme: galaxies that are enormous in size yet nearly empty within. Some of the most unsettling galaxies are not those that grew too fast, but those that seem barely there at all. Ultra-diffuse galaxies challenge a basic intuition. When we imagine a large galaxy, we imagine a dense one, rich in stars, bright and gravitationally cohesive. Ultra-diffuse galaxies violate this expectation completely. In terms of physical size, many of these galaxies rival the Milky Way. Their stellar envelopes can stretch across similar diameters, but in terms of visible matter, they contain only a tiny fraction of the stars. Their light is spread so thinly that they are difficult to detect at all, often blending into the background of the sky. At first, their existence seemed paradoxical. A galaxy with so few stars should not hold itself together over cosmic time. Tidal forces from neighboring galaxies should tear it apart. Internal motions should disperse its stars. Yet ultra-diffuse galaxies persist. The key lies in what cannot be seen. These galaxies are dominated by dark matter. Their dark matter halos are massive enough to provide the gravitational glue that their sparse stellar populations lack. In some cases, dark matter outweighs visible matter by factors of hundreds or more. This flips a common assumption. In galaxies like the Milky Way, stars and gas dominate the visible structure, with dark matter providing a supportive framework. In ultra-diffuse galaxies, dark matter is the structure. Stars are secondary tracers faintly outlining an otherwise invisible system. Their origins remain debated. Some ultra-diffuse galaxies may be failed galaxy systems that acquired large dark matter halos but never formed many stars. Early feedback from supernovae or radiation could have expelled gas before star formation took hold. Others may be the remnants of larger galaxies stripped of their stars through repeated interactions, leaving behind a diffuse skeleton. Either scenario forces a reconsideration of what it means to be a galaxy. If size can be large while stellar content remains minimal, then brightness is no longer a reliable indicator of importance. Some of the largest galactic structures in the universe may be among the faintest. For an observer living within such a galaxy, the sky would look radically different. Stars would be sparse, The night would be darker, emptier, and less structured. The sense of belonging to a dense stellar system would be absent. Ultra-diffuse galaxies reveal that structure does not require abundance. Stability does not require brilliance. A galaxy can be vast and yet almost empty. And if galaxies can exist with stars reduced to a trace, then it is possible to imagine systems where stars are not merely rare but nearly absent. That possibility leads to the next extreme, where galaxies fade almost entirely into darkness. Some galaxies push the concept of faintness even further. They are not merely dim, they are almost entirely invisible. Dark galaxies are systems that contain large amounts of gas and dark matter yet form few or no stars. Without starlight to illuminate them, they do not announce their presence in images of the sky. They reveal themselves only indirectly through their gravitational influence, or through faint radio signatures emitted by cold hydrogen gas. For a long time, these galaxies were purely theoretical. Models of structure formation predicted that many dark matter halos should exist without ever becoming luminous. Gas could fall into these halos, but conditions might never allow it to cool and collapse into stars. Radiation from nearby galaxies, energetic feedback, or the internal dynamics of the halo itself could suppress star formation entirely. The challenge was detection. Without stars, dark galaxies blend seamlessly into the background of space. They do not glow. They do not outline their shape in visible light. If they existed, they would be effectively hidden from traditional surveys. Evidence began to accumulate through unconventional means. Radio telescopes detected clouds of neutral hydrogen, moving in ways that could not be explained by visible matter alone. In some cases, gravitational effects on nearby galaxies hinted at unseen mass. Tidal distortions appeared without an obvious luminous culprit. These signals suggested the presence of massive structures with little or no stellar component. Dark galaxies occupy a strange position in cosmic taxonomy. They meet some criteria for being galaxies. They are gravitationally bound, massive, and persistent. Yet they lack the defining feature most people associate with galaxies, stars. This blurs the boundary between categories. At what point does a dark matter halo become a galaxy? Is star formation required, or is gravitational coherence enough? Dark galaxies force astronomers to confront these questions directly. Their existence also carries broader implications. If dark galaxies are common, then the visible universe represents only a fraction of the galactic population. Many structures may exist unseen, shaping cosmic evolution without ever lighting up the sky. Interactions with these invisible systems could influence the growth and behavior of luminous galaxies, subtly altering their paths through space. In this view, darkness is not absence. It is unexpressed structure. Dark galaxies demonstrate that galaxy formation can fail, stall, or remain incomplete, not because matter is missing, but because conditions never align. The universe is capable of assembling massive systems that never ignite, and if galaxies can exist without stars, then the role of starlight in defining cosmic structure must be reconsidered. Yet even darkness does not represent the final extreme. There are galaxies where stars exist in abundance, but where another force dominates so completely that the rest of the galaxy becomes secondary. At the center of these systems lies the next extreme. In most galaxies, the central black hole is a background presence, massive, influential, but contained. In some galaxies, that balance collapses. These are systems where the growth of the central black hole has outpaced the growth of the galaxy itself. Instead of quietly orbiting within a stable stellar environment, the black hole becomes the dominant engine shaping the fate of everything around it. When a supermassive black hole actively feeds, it does not consume matter silently. Gas spiraling inward heats to extreme temperatures, releasing vast amounts of energy before crossing the event horizon. This process creates what astronomers call an active galactic nucleus, or AGN. In its most extreme form, the result is a quasar. Quasars can outshine entire galaxies. For a brief period, a region smaller than the solar system can emit more energy than hundreds of billions of stars combined. Radiation winds and jets erupt from the galactic core, extending thousands of light years into surrounding space. The consequences are profound. Gas that might otherwise form stars is heated or expelled. Shock waves disrupt molecular clouds. Entire regions of the galaxy are sterilized of star formation. In extreme cases, the black hole effectively throttles the galaxy that hosts it. This reverses an intuitive hierarchy. Instead of galaxies shaping their central black holes shape their galaxies. Observations show that some galaxies contain black holes that are unusually massive relative to their stellar populations. Their growth appears to have occurred early and rapidly before the rest of the galaxy had time to mature. These systems challenge the idea of coordinated, balanced evolution. Feedback becomes the defining feature. Energy released near the black hole does not remain confined. Jets punch through galactic disks. Radiation pressure drives gas outward. Over time, this feedback can halt star formation entirely, transforming an active galaxy into a quiet one. The Milky Way provides a stark contrast. Its central black hole is massive but currently dormant. It exerts little influence beyond its immediate surroundings. Star formation across the galaxy proceeds largely unaffected. This calm is not guaranteed elsewhere. Galaxies dominated by central black holes reveal how fragile balance can be. Small differences in early conditions, gas supply, merger timing. Angular momentum can tip a galaxy toward a radically different trajectory. Once feedback takes over, recovery becomes difficult. These systems highlight an uncomfortable truth. The fate of a galaxy can hinge on processes occurring at scales far smaller than the galaxy itself. In the universe, influence does not always scale with size, and if central dominance can reshape galaxies from within, then external forces can do the same from without. That brings us to another extreme: galaxies for which interaction is not an event but a permanent state. For many galaxies, interaction is a phase. For others, it is a condition that never ends. In dense regions of the universe, such as galaxy groups and clusters, galaxies do not live in isolation. They orbit within shared gravitational environments, passing close to one another repeatedly over billions of years. In these settings, stability is not the default outcome. Disruption is. Some galaxies appear to exist in a near-constant state of collision. Their structures are stretched into long tidal tails. Streams of stars arc outward, tracing past encounters. Gas is pulled from disks and compressed into knots where new stars ignite briefly before conditions change again. No single shape persists long enough to be considered final. These galaxies are not snapshots of transition. They are systems without equilibrium. Repeated interactions prevent them from settling into stable configurations. Each close pass rearranges, mass redistributes angular momentum, and alters internal dynamics. Even when mergers do not fully complete, the cumulative effect is transformative. Star formation in these environments becomes erratic. Bursts ignite when gas is compressed during encounters. Then feedback and stripping shut them down. New bursts follow as fresh material is driven inward by subsequent interactions. The result is a galaxy whose evolution is governed by external forces rather than internal regulation. In such systems, history never finishes writing itself. Some galaxies are caught in extended mergers, where two or more systems intertwine for billions of years before fully coalescing. Their identities blur, boundaries dissolve. What constitutes a single galaxy becomes ambiguous. This ambiguity is not merely visual. Kinematic studies reveal stars moving on complex overlapping trajectories. Gas flows reverse direction. Dark matter halus interpenetrate. The distinction between host and intruder fades with time. From within, such a galaxy would be a place of perpetual change. The stellar sky would shift subtly over cosmic timescales. Regions of star formation would ignite and fade unpredictably. Long-term stability. The quiet persistence seen in the Milky Way would be absent. These galaxies demonstrate that collision is not an anomaly in the universe. It is a common mode of interaction, especially where matter is concentrated. Over cosmic time, many galaxies experience repeated disruption rather than isolated events. The Milky Way has not escaped interaction. It has absorbed smaller galaxies and bears the faint signatures of past encounters, but it has avoided prolonged entanglement. That avoidance may be critical. Galaxies in permanent collision show that without extended periods of calm structure never settles. Evolution becomes a continuous response to disturbance rather than a progression toward balance. At this extreme, the very concept of a stable galaxy begins to dissolve, which leads to a final question. If galaxies can be early massive empty dark dominated from within, or reshaped endlessly from without, then what exactly defines a galaxy in the first place? That question marks the edge of our current understanding. After confronting galaxies that are too early, too massive, too empty, too dark, too violent, or too unstable, astronomers arrive at an unexpected impasse. The problem is no longer observation, it is definition. For much of modern astronomy, a galaxy was treated as a familiar object, a gravitationally bound system of stars, gas dust, and dark matter. This definition worked well when most known galaxies resembled the Milky Way or its close relatives. Extreme galaxies strain every part of that description. Some systems are dominated by dark matter and gas with almost no stars. Others contain stars but lack long-term stability. Some are so diffuse that their stellar populations barely trace a coherent structure. Others blur into their surroundings through continuous interaction. At what point does a system stop being a galaxy? Is a dark matter halo without stars a galaxy or merely a potential one? Is a merging system still a galaxy if it never settles into a stable form? Is a quasar-dominated system defined by its stars or by its black hole? These questions are not semantic. They affect how astronomers count galaxies, model cosmic evolution, and interpret large-scale structure. If definition shifts, so do statistics. If boundaries blur, so do conclusions. In practice, astronomers rely on operational criteria. Gravitational binding matters, longevity matters, coherence matters, but none of these criteria alone is sufficient. Extreme galaxies often satisfy some conditions while violating others. This suggests that galaxy is not a single category but a spectrum. At one end lie systems like the Milky Way, stable, star-forming and well-ordered. At the other end lie dark halos, disrupted mergers and transient structures that barely fit within traditional frameworks. Between them exists a continuous range of possibilities. This spectrum reflects a deeper truth about the universe. Cosmic structures are not designed to fit human classifications. They emerge from physical processes that do not prioritize neat boundaries. Gravity assembles matter where it can. Feedback reshapes it. Environment perturbs it. The result is complexity without obligation to clarity. In this context, extreme galaxies are not exceptions. They are natural outcomes of flexible rules applied under varied conditions. The Milky Way once again occupies a narrow region of this spectrum. It sits far from the edges where definitions fail. Its familiarity has shaped expectations that the universe never promised to satisfy. Recognizing this does not weaken astronomy. It strengthens it. It forces models to accommodate diversity rather than suppress it. It shifts focus from idealized cases to full distributions. It acknowledges that understanding the universe requires embracing its messiness. And once that perspective is adopted, one conclusion becomes unavoidable. Extremes are not peripheral to cosmic evolution. They are central to it. The most extreme galaxies in the universe do not exist in isolation from cosmic history. They shape it. Early forming galaxies accelerate chemical enrichment. Massive systems influence large-scale structure. Dark galaxies alter gravitational landscapes invisibly. Black hole-dominated galaxies regulate star formation across entire regions. Colliding systems redistribute matter and energy over vast scales. Together, these extremes drive evolution forward. They reveal how flexible galaxy formation can be, how quickly assumptions can fail, and how narrow our intuitive expectations truly are. They show that the universe does not converge toward a single outcome. It explores possibilities. In that exploration, balance is rare, stability is conditional, familiarity is accidental. The Milky Way survives not because it represents the rule, but because it occupies a fortunate corridor between extremes. It avoided early collapse. It avoided violent dominance. It avoided prolonged disruption. That path is not guaranteed, and it is not common. Part 3 ends with this realization. Galaxies are not variations on a theme. They are outcomes of a process that tolerates and often favors extremes. And once that is understood, a new question takes center stage. If galaxies differ this radically in structure, history, and environment, then what does that mean for the possibility of life within them? In the next part, the journey shifts from structure to consequence. Could life exist in other galaxies in the universe? That question can only be asked now after we've seen just how extreme the cosmic landscape truly is. When people ask whether life exists elsewhere in the universe, they almost always start with planets. Is there liquid water? Is the temperature right? Is the atmosphere stable? These questions matter, but they are incomplete. Planets do not exist in isolation. They orbit stars, and stars are born, evolve, and die inside galaxies. Every planetary system inherits the conditions of its galactic environment long before life has a chance to appear. For a long time, this context was ignored. The search for life focused on local factors as if the wider universe were merely a backdrop. But galaxies are not passive stages. They regulate radiation, control stellar density, and determine how often catastrophic events disrupt long-term stability. In some galaxies, stars are packed so tightly that nearby supernovae are common. In others, violent bursts of star formation flood entire regions with radiation. Some galaxies are calm for billions of years. Others never experience a quiet epoch at all. These differences matter. Life does not require perfection, but it does require time. Time to assemble complex chemistry. Time to adapt. Time to persist without being erased by repeated cosmic upheaval. If galaxies vary this dramatically, then the question of life cannot be universal. It must be conditional. In this part of the journey, we move beyond the familiar question of habitable planets and confront a deeper one. Not where life might exist, but where it could survive. Because before life can emerge on a world, it must first endure the galaxy that surrounds it. And not all galaxies offer the same chance. Life does not arise in a vacuum. It inherits the environment that exists long before the first molecule begins to replicate. Every star system forms within a galaxy, and that galaxy sets the background conditions under which planets and life must operate. Stellar density, radiation levels, chemical composition, and long-term stability are not random variables. They are products of galactic-scale processes. The Milky Way illustrates this clearly. Its stars are spaced far enough apart that catastrophic events are rare on planetary timescales. Supernovae occur, but typically at distances that do not sterilize entire regions. Heavy elements, carbon, oxygen, iron, are abundant enough to build rocky planets and complex chemistry, and the galaxy has remained relatively stable for billions of years. None of this is guaranteed elsewhere. In galaxies with higher stellar densities, stars form closer together. This increases the frequency of nearby supernovae and gravitational disturbances. Planetary orbits can be perturbed, radiation levels rise. Long-term stability becomes harder to maintain. Other galaxies struggle with chemistry. Galaxies that formed early or that lost gas quickly may lack sufficient heavy elements to form Earth-like planets in the first place. Without multiple generations of star formation, the raw materials for complex molecules remain scarce. Time itself is another constraint. Life requires extended periods without catastrophic interruption. Repeated bursts of star formation, frequent mergers, or active galactic nuclei can reset conditions faster than biology can adapt. Even if life emerges, it may never reach complexity. These factors combine into what astronomers call galactic habitability. This concept shifts the focus from individual planets to environments. It asks not whether a planet can support life briefly, but whether a galaxy can support life for long enough to matter. In this framework, the Milky Way appears unusually accommodating. Its balance of activity and calm has persisted across billions of years. That persistence may be critical, but it also raises an uncomfortable implication. If galactic conditions vary widely, then habitable worlds may be unevenly distributed across the universe. Life could be common in some galaxies and nearly impossible in others. Understanding where life might exist therefore requires understanding galaxies themselves. And among the many galactic factors that influence habitability, one stands out above all others: radiation. Radiation is not always dramatic. It does not announce itself with explosions or visible destruction. Yet over long periods it may be the most decisive factor in determining whether life can persist. On galactic scales, radiation comes from many sources. Supernovae release intense bursts of high-energy particles. Gamma-ray bursts emit narrow beams capable of sterilizing entire regions of a galaxy. Active galactic nuclei flood their surroundings with radiation when central black holes feed. Even ordinary stars contribute a background of ultraviolet and cosmic rays. In moderation, radiation is manageable. In excess, it becomes hostile. Galaxies with high star formation rates tend to be dangerous environments. Massive stars form, quickly burn intensely, and die young. Their deaths produce frequent supernovae, raising radiation levels across large volumes of space. Planets orbiting stars in these regions may be repeatedly exposed to radiation, capable of stripping atmospheres or disrupting complex chemistry. Starburst galaxies represent an extreme case. In these systems, star formation occurs so rapidly that supernovae overlap in time and space. Radiation fields remain elevated for millions of years. The cumulative effect is not a single catastrophic event, but a persistent hostile background. Life, if it emerged at all, would struggle to survive long enough to diversify. Dense stellar environments amplify the risk. When stars are packed closely together, the average distance to a supernova decreases. Events that would be harmless in a sparse galaxy become lethal in a dense one. Even without explosions, gravitational interactions can perturb planetary orbits, exposing worlds to unstable climates and fluctuating radiation from their host stars. Gamma-ray bursts add another layer of uncertainty. These rare but powerful events can affect regions thousands of light-years across. In galaxies with high rates of massive star formation, gamma-ray bursts may occur more frequently. This single, well-aimed burst could sterilize large swaths of a galaxy, resetting biological clocks on countless worlds simultaneously. The Milky Way appears to occupy a safer zone. Its star formation rate is moderate. Massive stars are relatively dispersed. Gamma-ray bursts are rare in its current epoch. While radiation events do occur, they are infrequent enough that long periods of biological stability remain possible. This balance is not universal. Some galaxies are too active, others are too compact. Some experience repeated energetic episodes driven by central black holes. In these environments, radiation acts not as an occasional threat, but as a constant pressure against complexity. Radiation does not prevent life from beginning. It prevents life from enduring. Understanding galactic habitability therefore requires more than counting planets. It requires mapping radiation histories over billions of years. Only galaxies that offer long-term shelter from extreme radiation provide a stable foundation for complex life. And radiation is only one piece of the puzzle. Even in galaxies where radiation levels are low, another requirement must still be met: time. Life does not simply need protection from sudden destruction. It needs continuity. Biological complexity emerges slowly, from simple chemistry to self-replicating molecules, from single-celled organisms to ecosystems capable of sustaining diversity. Each step requires time measured in hundreds of millions or billions of years. This process assumes that conditions remain within survivable limits long enough for adaptation to occur. Not all galaxies offer that stability. In chaotic galaxies, large-scale disturbances are frequent. Repeated mergers reshape stellar orbits. Gas flows are disrupted. Star formation turns on and off in unpredictable bursts. Planetary systems formed under one set of conditions may find themselves in a radically different environment within a relatively short cosmic interval. These disruptions do not need to be violent to be harmful. Small gravitational perturbations can alter planetary orbits, changing climates over geological timescales. Shifts in stellar neighborhoods can expose planets to new radiation sources. Even gradual changes can destabilize environments faster than life can adapt. Galaxies in dense clusters are particularly challenging. In these regions, galaxies interact repeatedly with their neighbors and with the surrounding intracluster medium. Gas can be stripped away. Star formation can be quenched abruptly. Orbits within galaxies can be disturbed by tidal forces. Stability becomes a temporary condition rather than a long-term guarantee. By contrast, galactic calm creates opportunity. Galaxies that experience long intervals without major mergers allow planetary systems to remain dynamically stable. Stellar neighborhoods change slowly. Radiation backgrounds fluctuate within tolerable ranges. Under these conditions, biological processes can accumulate complexity rather than constantly resetting. The Milky Way appears to have benefited from such calm. While it has absorbed smaller galaxies and bears the faint signatures of past interactions, it has avoided major disruptive mergers for billions of years. Its disk has remained intact. Its star formation has proceeded at a relatively steady pace. This continuity may be one of its most important features for life. Calm does not mean inactivity. Stars still form, supernovae still occur, but these events are spread out in space and time, allowing ecosystems to recover and adapt. The galaxy provides not perfection but predictability. Chaos, by contrast, compresses time. In galaxies dominated by frequent interactions or rapid internal change conditions evolve too quickly. Even if life emerges, it may never persist long enough to reach complexity. Biological experiments are started then erased again and again. This contrast suggests that galactic habitability is not determined solely by present conditions but by history. A galaxy may look calm today yet have endured violent upheavals in its past. Another may appear chaotic but eventually settle into stability, for life timing matters as much as environment. The question is not simply whether a galaxy can host life now, it is whether it can host life continuously without interruption for billions of years, and even when calm persists, another challenge remains. Not all galaxies provide the raw materials life requires. That challenge becomes especially clear when we consider galaxies dominated by old stars. Elliptical galaxies seem at first glance like unlikely places to search for life. They are dominated by old stars. Star formation has largely ceased. Cold gas, the raw material for building new stars and planets, is scarce or absent. Compared to spiral galaxies, ellipticals appear quiet, static, and chemically exhausted. And yet this apparent barrenness is deceptive. Most elliptical galaxies form their stars early during intense bursts of activity billions of years ago. In that early phase, they produced vast numbers of stars and with them large quantities of heavy elements. Carbon, oxygen, silicon, and iron were forged and dispersed long before star formation shut down. This means that planetary systems could already exist. If planets formed during those early epochs, they may have persisted ever since orbiting long-lived low-mass stars that remain stable for tens of billions of years. In such systems, the absence of ongoing star formation may actually be an advantage. Elliptical galaxies are in many respects calmer than spirals. Supernovae are rare, massive stars are scarce, radiation backgrounds are low, central black holes, while often massive, are frequently inactive. The energetic events that threaten long-term biological stability occur less often than in actively star-forming galaxies. For life that already exists, this calm could be beneficial. Long-lived stars provide stable energy output. Planetary orbits experience little disturbance from nearby stellar explosions. Galactic-scale conditions change slowly, allowing biological processes to proceed without frequent interruption. The challenge lies at the beginning. If elliptical galaxies lack ongoing star formation, then the window for creating new habitable worlds may have closed long ago. Life would need to arise early during the galaxy's formative phase and survive through billions of years of gradual fading. This shifts the question. Elliptical galaxies may not be good at creating life now, but they may be capable of preserving life for extraordinarily long periods. In this scenario, life would be ancient. Civilizations, if they existed, could have emerged long before the sun was born. Their stars would be older. Their planetary systems would have had more time to evolve. Their biology could be shaped by environments that have remained unchanged for eons. There are also limitations. Elliptical galaxies tend to be denser than spirals. In their cores, stellar densities can be high enough to increase the risk of gravitational disturbances, but in their outer regions, conditions may be far more benign, quiet, spacious, and stable. This creates a nuanced picture. Elliptical galaxies are not universally hostile to life. They are selectively challenging. They favor longevity over renewal, preservation over opportunity. Life there would be rare, ancient, and difficult to detect, but not impossible. The possibility forces a broader realization. Habitability is not tied to youth or activity. It can emerge from calm, from age, and from endurance. And when we move away from massive galaxies altogether, the picture shifts once again. Smaller galaxies pose an entirely different set of problems. Smaller galaxies may seem at first like simpler environments. Fewer stars, less mass, less activity. But when it comes to life, simplicity does not translate to safety. Dwarf galaxies and irregular systems dominate the universe numerically. They are the most common type of galaxy by far, yet their physical properties create some of the most hostile conditions for long-term habitability. The core problem is gravity. Low-mass galaxies possess shallow gravitational wells. They struggle to hold onto gas, especially when energetic events occur. A single burst of star formation can heat and expel large fractions of a galaxy's gas supply. Once lost, that gas may never return. This has direct consequences for chemistry. Heavy elements. The building blocks of rocky planets and complex molecules are produced by stars and distributed through supernovae. In small galaxies, much of this enriched material escapes into intergalactic space. Chemical evolution proceeds slowly and inefficiently. The raw materials required for life remain scarce. Radiation compounds the difficulty. Because stars are packed into smaller volumes, a supernova in a dwarf galaxy affects a larger fraction of the system. There is less distance for radiation to dissipate. Entire regions may be sterilized repeatedly. Recovery time becomes short, but interruptions are frequent. Irregular galaxies intensify these challenges. Their chaotic structure leads to uneven star formation. Some regions ignite in bursts while others remain dormant. Planetary systems may form in environments that later become hostile as conditions shift unpredictably. Long-term stability is hard to maintain. Even shielding is limited. Large spiral galaxies offer protective niches regions far from dense star-forming cores, where radiation levels are lower and disturbances are rarer. Small galaxies lack this internal diversity. There are fewer safe zones, and those that exist may not persist. From a biological perspective, this creates a harsh filter. Life might arise in small galaxies, but sustaining it over billions of years becomes extraordinarily difficult. The combination of poor chemical enrichment, frequent radiation exposure, and environmental volatility works against complexity. The Milky Way once again appears privileged by comparison. Its mass allows it to retain gas and metals. Its size creates gradients, inner regions more active, outer regions more stable. Life does not need the entire galaxy to be calm. It only needs a long-lived refuge. Small galaxies rarely provide that refuge. This does not mean they are empty of possibility. It means that the odds are stacked against them. Life, if it exists, that would be resilient, simple, and likely short-lived on cosmic timescales. As we compare environments across galaxy types, a pattern begins to emerge. Life does not require perfection, but it does require a narrow window of conditions. That realization brings us to the central question of this part. Does life require a galaxy like the Milky Way at all? By this point, a pattern has become difficult to ignore. Galaxies that are too small struggle to retain the ingredients life needs. Galaxies that are too active expose their worlds to constant disruption. Galaxies that are too chaotic reset conditions faster than biology can adapt. This naturally raises a deeper question. Is the Milky Way simply one example among many? Or does life require something like it? At first glance, the Milky Way seems to occupy a narrow and fortunate corridor. It is massive enough to hold on to gas and heavy elements, yet not so dense that radiation events become frequent and lethal. Its star formation rate is moderate. Its disk is stable. Its central black hole is quiet. Its merger history has been relatively gentle. These traits are not independent. Together, they create an environment that balances renewal and stability. New stars and planets continue to form while long-lived systems remain undisturbed for billions of years. Chemical enrichment proceeds efficiently but not violently. Radiation exists but not at overwhelming levels. This balance may be rare, however rarity does not imply exclusivity. Other galaxies can share similar properties without being exact copies of the Milky Way. Some spiral galaxies are slightly larger or smaller, slightly more active or more quiescent, yet still maintain extended periods of calm. Some elliptical galaxies may offer stable environments long after their active phases have ended. Even certain irregular galaxies may contain localized regions of relative safety. The key is not shape, it is history. Life appears to require a long window of continuity, billions of years, during which catastrophic events are infrequent enough for complexity to accumulate. A galaxy does not need spiral arms to provide that window. It needs predictability, chemical richness, and time. In this sense, the Milky Way is not unique because it is perfect. It is fortunate because it avoided extremes. It did not burn too fast. It did not fragment too often. It did not exhaust its resources too early. This reframes the idea of galactic habitability. Rather than asking which galaxies look like ours, the more useful question becomes which galaxies follow similar evolutionary paths. Paths that preserve stability without eliminating renewal. Paths that allow life to begin, persist, and diversify. Such paths may exist across many galaxy types, but they are constrained. They occupy a narrow band within a much wider landscape of hostile possibilities. This suggests an unsettling conclusion. Life may not be rare because biology is difficult. It may be rare because suitable galactic histories are uncommon. If that is true, then life across the universe may be unevenly distributed, clustered within a subset of galaxies that happen to evolve gently enough long enough to permit it. And even if life does arise in those galaxies, another challenge remains: detection. Because knowing that life could exist is very different from ever being able to confirm that it does. Even if life exists in other galaxies, confirming it may be one of the hardest challenges science has ever faced. The distances involved are overwhelming. Individual stars in other galaxies are faint. Planets around those stars are effectively invisible with current technology. Even the most powerful telescopes can only study other galaxies in aggregate blended light from billions of stars compressed into a single signal. This makes traditional biosignatures nearly impossible to detect. On nearby exoplanets, scientists search for atmospheric gases that suggest biological activity. Oxygen, methane, and other chemical imbalances can hint at life. But across galactic distances, these signals vanish into noise. The combined light of an entire galaxy overwhelms the subtle fingerprint of any single inhabited world. In principle, a sufficiently advanced civilization might leave detectable traces. Large-scale energy use could alter a galaxy's infrared output. Unusual spectral features might indicate artificial activity. These ideas motivate searches for technosignatures rather than biosignatures, evidence of technology rather than biology. But even these signals face severe limitations. Natural astrophysical processes can mimic many of the same effects. Dust star formation and black hole activity all produce strong infrared emissions. Distinguishing artificial patterns from natural ones across millions of light years becomes a problem of interpretation rather than detection. Silence, therefore, is ambiguous. The absence of evidence does not imply the absence of life. It may simply reflect the limits of observation. Life in other galaxies could be widespread yet forever beyond our ability to confirm. This creates a sobering perspective. Life might not be rare in the universe. It might be isolated by distance. Civilizations could rise and fall in other galaxies without ever knowing we exist, just as we may remain forever unaware of them. The universe could be filled with biology, history, and complexity, each confined to its own island of causality. In this context, the Milky Way becomes more than a home. It becomes the boundary of our direct knowledge. Everything beyond it is inferred, modelled, and imagined, but never touched. Other galaxies may host life, but they may also remain permanently silent to us. This does not diminish the significance of the question. It sharpens it, because it reminds us that science is constrained not only by what exists, but by what can be known. And that realization leads naturally to the final perspective of this series. The question of life in other galaxies does not end with a simple yes or no. What the science suggests is something more nuanced. Life does not require extraordinary circumstances, but it does require a precise alignment of conditions sustained over long periods of time. Those conditions are not set by planets alone. They are shaped by galaxies, by their mass history, stability, and environment. Some galaxies provide that foundation. Many do not. The Milky Way appears to sit within a narrow corridor of galactic evolution that favors complexity. It is not perfect. It is not uniquely designed for life, but it has been calm, enriched, and stable for long enough to allow biology to unfold. Other galaxies may share similar corridors. Others may never offer them at all. This reframes how we think about life in the universe. Life may be widespread in principle, yet uneven in reality. Concentrated in galaxies that evolve gently, quietly, and patiently, absent or fleeting in galaxies shaped by extremes. And even when life does exist, distance imposes a final barrier. Across intergalactic space communication may be impossible. Confirmation may never arrive. Other galaxies may remain forever out of reach, not just physically, but epistemologically. Which brings us to the final question of this journey. If most galaxies are beyond our ability to visit, communicate with, or even confirm life within, what does it mean to live inside one small galaxy surrounded by trillions of others we can never reach? That question defines the final step beyond home, other galaxies beyond reach, the ultimate cosmic limit. We live in a universe filled with galaxies we will never touch. This is not a statement about technology. It is not a failure of ambition, engineering, or imagination. Even with perfect propulsion, unlimited energy, and infinite time, most galaxies remain permanently inaccessible. The reason is not distance alone. It is motion. The universe is expanding, and that expansion is not slowing down. Space itself is stretching, carrying galaxies away from one another in a way that no signal, no spacecraft, and no influence can outrun. Beyond a certain boundary, separation becomes absolute, and yet we can see them. Telescopes reveal galaxies billions of light years away. We measure their shapes, their masses, their star formation histories. We know when they formed and how they evolved. We can describe them in detail even as we accept that they are forever beyond reach. This creates a strange contradiction at the heart of modern cosmology. There are parts of reality that are real, measurable, and well understood, and yet permanently unreachable, not because they are hidden, but because the universe itself prevents contact. In this final part of the journey, we confront the ultimate limit. Not the limit of human curiosity, but the limit imposed by space-time. We explore what it means to live inside a cosmic horizon, where knowledge extends farther than access and understanding does not imply connection. Other galaxies are not just distant places. They are reminders that the universe contains more than we can ever interact with. and that fact changes how we understand our place within it. When we speak about the universe, we often do so as if it were fully available to us, as if everything that exists is, at least in principle, something we could eventually see, study, or reach. That assumption is false. What we observe is not the universe itself. It is only the part of the universe that has had time to reveal itself to us. This region is known as the observable universe. Its boundary is not a physical wall. There is no edge in space where matter suddenly stops. Instead, it is defined by time. Light travels at a finite speed and the universe has a finite age. There are regions so distant that their light has not yet had enough time to reach us since the beginning of cosmic expansion. Those regions exist. They are simply causally disconnected from us. The observable universe spans roughly 93 billion light-years in diameter. This number already defies intuition, but even this vast volume represents only a portion of what exists. Beyond it lies more space, more matter, and more galaxies arranged according to the same physical laws yet permanently unseen. The distinction between existence and observability is crucial. A galaxy does not need to be visible to be real. Its reality does not depend on our ability to detect it. Observability is a property of space-time geometry, not of the object itself. In fact, many galaxies that exist right now have never sent us a single photon. Their light is still traveling through expanding space stretched and delayed by cosmic time. Some will eventually enter our horizon, others never will. This introduces a humbling constraint on knowledge. Cosmology does not describe everything that exists. It describes everything that can in principle affect us. The observable universe is not a map of total reality. It is a record of causal contact, a boundary drawn not by ignorance but by the structure of space-time itself. And as the universe continues to expand, that boundary does not remain fixed. It changes, which means that distance alone does not determine what is beyond reach. Expansion does, and that expansion transforms separation into something far more final. Distance in the universe is not static. It is not a simple measure of how far apart objects are at a given moment. It is something that evolves with time. As the universe expands, space itself stretches. Galaxies are not moving through space away from us in the usual sense. Instead, the space between us and them is growing. Over vast scales, this expansion dominates all other motion. This distinction matters. In an expanding universe, separation can increase faster than any signal can travel. Beyond a certain distance, the rate at which space expands exceeds the speed of light. Not because anything is breaking physical laws, but because those laws apply to motion through space, not to the expansion of space. When that threshold is crossed, contact becomes impossible. Light emitted today from galaxies beyond this limit will never reach us. No future signal, no matter how long we wait, can close the gap. The expansion continuously adds new space between us and the source faster than light can traverse it. This creates what cosmologists call a cosmic event horizon. Unlike the observable universe, which is defined by past light, the event horizon is defined by the future. It marks the boundary beyond which events can never influence us no matter how long the universe exists. Many galaxies we see today are already near this boundary. Their light reaches us only because it was emitted long ago when they were closer. As time passes, those galaxies continue to recede. Eventually, even the light they emit now will be carried away by expansion never arriving. Separation becomes permanent. This is why faster travel does not solve the problem. Even hypothetical spacecraft moving arbitrarily close to the speed of light would still be embedded in expanding space. They had not outrun the growth of the universe itself. Expansion transforms distance into destiny. Two regions of space can share a common origin, obey the same laws, and yet become forever isolated simply because the geometry between them changes. Causality, not curiosity, defines the limits of interaction. This realization reframes what far away means in cosmology. Some galaxies are distant but reachable in principle. Others are distant in a deeper sense, separated not by space alone but by time and expansion. They are not just far, They are gone in every practical sense, even as their ancient light still arrives. And that leads to an unsettling truth. There are galaxies we can study in a detail map with precision and understand scientifically, yet will never under any circumstance reach. Some of the most distant galaxies we observe occupy a peculiar category. They are visible, they are measurable, and yet they are unreachable. Their light has crossed billions of light years to arrive here. From that light, astronomers extract extraordinary detail. We measure their mass estimate, their star formation rates, identify the elements within them, and reconstruct their evolutionary histories. In every scientific sense, these galaxies are known to us, but knowledge does not imply access. Because while their ancient light is still arriving, the galaxies themselves are no longer where that light began its journey. Expansion has carried them far beyond their original positions. The space between us and them has grown so much that no future signal we send could ever catch up. This creates a paradox unique to cosmology. We can observe objects that we will never influence, never visit, and never communicate with. They exist within our past light cone, but outside our future one. The connection is one-way, locked in time. These galaxies are not rare edge cases. A significant fraction of the galaxies detected in deep field surveys fall into this category. They are close enough in a temporal sense for their early light to reach us, but they are already too distant in an expanding sense for any future interaction to occur. This means the universe contains places that are scientifically accessible but physically forbidden. In everyday experience, seeing implies potential contact. In cosmology, that intuition fails. Vision does not guarantee reachability. Observation does not guarantee causation. The distinction matters because it reshapes what exploration means. We often imagine exploration as a journey outward, a gradual extension of reach. But in the universe, exploration is asymmetrical. We receive information from regions we can never approach. We study environments that will forever remain abstract. The galaxies we see are not destinations. They are messages. Each photon carries a snapshot of a region of space as it once was, not as it is now. Over time, these messages thin out. The expansion of space stretches wavelengths, dims brightness, and reduces the flow of information. Eventually, even observation becomes impossible. This makes the present moment unusually rich. We live at a time when the universe is old enough to have formed vast structures, yet young enough that their light still reaches us. Many galaxies remain visible now that will not be visible in the far future. In that sense, reachability is not just about distance. It is about timing. And timing determines not only what we can reach, but what we can ever know. Which leads to a quieter, more sobering realization. Some galaxies have already crossed a boundary from which even their light will no longer arrive. Not all galaxies we know about are still visible. Some have already crossed a boundary from which no new light will ever reach us. Because the universe is expanding at an accelerating rate, there exists a limit beyond which emitted light is permanently carried away by the growth of space itself. When a galaxy passes beyond this cosmic event horizon, any photons it emits afterward are lost to us forever. What remains is only the last light it sent before crossing that boundary. In practical terms, this means that some galaxies are already gone, not destroyed, not extinguished, but causally disconnected. They continue to exist to form stars to evolve according to the same laws of physics, but their future has been sealed off from our awareness. We will never see what they become. The light we currently receive from these galaxies is a kind of afterimage. It represents a final glimpse into a region of space that is no longer in contact with us. As time passes, even that afterimage fades. The remaining photons arrive increasingly redshifted, stretched to longer wavelengths diluted by expansion. Eventually, the signal falls below detectability. This process does not happen all at once. It unfolds gradually over billions of years. Galaxies do not blink out of existence. They dim redden and slip quietly beyond observation. From the perspective of future observers in our own galaxy, these systems will simply never have existed. There will be no evidence of them in the sky, no trace in the cosmic background, No indication that the universe was ever larger or more populated than what remains visible. The observable universe will contract not because space shrinks, but because information disappears. This introduces a subtle but profound idea. Knowledge itself has a horizon. There are facts about the universe that are true now but will not remain knowable forever. Observations available to us today will be inaccessible to observers born tens of billions of years from now. The universe does not merely evolve physically, it evolves epistemologically. We live at a privileged moment, not because we are special, but because the timing is favourable. The universe has expanded enough to reveal its large-scale structure, but not so much that those structures have vanished from view. Galaxies that have already disappeared remind us that this window will not remain open. And as the window closes, the universe ahead becomes quieter, emptier, and more isolated, which brings us to the long-term future of cosmic reach, a future in which even the idea of distant galaxies becomes a memory. As cosmic expansion continues, the universe does not become more complex. It becomes quieter. Over tens of billions of years, galaxies beyond our local region will fade from view one by one. Their light will stretch to wavelengths too long to detect. Their brightness will fall below any conceivable sensitivity. Eventually, the sky will empty itself of distant structure. What will remain is the local group. The Milky Way, Andromeda, and a small collection of nearby dwarf galaxies are gravitationally bound. Expansion cannot pull them apart. Over time, they will merge into a single massive system. For future observers living within it, this merged galaxy will appear to be the entire universe, and nothing beyond it will be visible. This creates a striking inversion of perspective. Early in cosmic history, observers could see little because structure had not yet formed. In the far future, observers will see little because structure has receded beyond reach. The universe will appear small, static, and isolated, not because it truly is, but because information has been lost. From within that future galaxy, there will be no direct evidence of cosmic expansion, no distant galaxies rushing away, no redshift patterns revealing a dynamic universe. The sky will contain stars, gas, and perhaps a faint remnant of background radiation, but no obvious sign of a larger cosmos. Cosmology will become extraordinarily difficult. Future scientists, even if intelligent and curious, will struggle to infer that the universe was once filled with countless galaxies. The evidence we rely on today, deep field images, large-scale surveys, precise measurements of expansion, will no longer be available. This is not speculation. It is a consequence of known physics. Accelerated expansion ensures that the observable universe shrinks over time, not in size but in content. Information drains away. Structure becomes local. Isolation becomes the dominant condition. In this future, the concept of other galaxies may not exist. Not because they never did, but because they can no longer be seen. The irony is difficult to ignore. We live in a universe vast enough to humble us, yet at a time when its vastness is still visible. The loneliness of the future universe will not be felt emotionally. It will be built into the fabric of observation, and that loneliness carries an important lesson. Our understanding of the universe is not guaranteed. It depends on when we happen to exist, which raises a deeper question. If expansion isolates regions so completely, could faster travel or advanced technology ever overcome this fate? Or is the separation truly absolute? It is tempting to imagine that the problem of cosmic separation could be solved with better technology, faster spacecraft, more efficient engines, exotic propulsion systems that approach the speed of light. But the barrier we face is not a technological one. It is geometric. No matter how fast a spacecraft travels through space, it remains embedded within space as it expands. The expansion of the universe is not something that can be outrun because it is not motion in the usual sense. It is the continuous creation of new distance between regions. Beyond the cosmic event horizon, space expands faster than light can cross it. This does not violate relativity because relativity limits the speed of objects moving locally through space. It does not restrict how fast space itself can stretch. Once a galaxy crosses that horizon, the gap between us and it grows faster than any signal can traverse. Even a hypothetical probe moving arbitrarily close to the speed of light would fail. As it travels, new space would continue to form ahead of it. The destination would recede faster than the probe could advance. The journey would not merely be long, it would be futile. This eliminates a common misconception. The unreachable regions of the universe are not unreachable because they are too far away right now. They are unreachable because the structure of space-time ensures that the separation will always increase. There is no shortcut, no waiting period after which access becomes possible, no technological breakthrough that changes the geometry of the universe. This boundary is permanent. In practical terms, this means that the universe is divided into causally isolated regions. Each region can influence itself but not others beyond its horizon. What happens there can never affect us, and what happens here can never affect them. From a cosmic perspective, this is a form of isolation built into reality. Civilizations may arise in distant galaxies, develop technology, and explore their local environments. But no matter how advanced they become, they will remain confined to their own causal islands. The universe does not allow information to cross certain boundaries. This realization reframes the meaning of exploration. Exploration is not limited by courage or intelligence. It is limited by causality. And if travel cannot bridge these gaps, perhaps communication can. That possibility leads to another question. Even if we cannot reach other galaxies, could we at least exchange information with civilizations beyond our horizon? Or is silence inevitable? If travel cannot overcome cosmic separation, communication seems like a more modest hope. Signals require far less energy than spacecraft. Light radio waves and other forms of electromagnetic radiation travel at the fastest speed allowed by physics. If anything can cross the universe, it should be information. But the same boundary applies. The cosmic event horizon does not discriminate between matter and messages. A signal sent today from beyond that horizon will never reach us. A signal we send will never arrive there. The separation grows faster than the signal can propagate. This makes the silence of the universe deeply ambiguous. We often interpret silence as absence. No signals detected, no messages received, no clear evidence of other civilizations. But on cosmic scales, silence may be enforced, not chosen. Civilizations could exist in enormous numbers beyond our horizon, each broadcasting, listening and wondering if they are alone just as we do. Their signals may fill their local regions of space, yet never cross the expanding gulf that separates causal domains. From our perspective, they are indistinguishable from nothing at all. Even within the observable universe, communication is fragile. Signals weaken with distance. They are drowned out by cosmic noise. They disperse over time. Across intergalactic distances, even the most powerful transmissions fade into background radiation. Beyond the horizon, communication is not merely difficult, it is forbidden. This has profound implications for how we think about cosmic loneliness. The universe may not be empty of intelligence. It may be fragmented, divided into isolated islands of awareness, each with its own history, discoveries and questions, yet permanently unable to share them. This is not a pessimistic conclusion, it is a structural one. Reality itself imposes limits on connection. Understanding this reshapes the meaning of the search for life. We are not just searching for neighbours, we are searching within a shrinking window of causal overlap bounded by expansion and time. Which brings us to the edge of what science can meaningfully address. When parts of reality exist beyond verification, beyond influence, and beyond communication, how does science proceed? That question defines the final stretch of this journey. Science is often described as the pursuit of what exists. In practice, it is the pursuit of what can be tested. This distinction becomes critical at cosmic scales. There are regions of the universe that almost certainly exist, governed by the same physical laws, filled with the same kinds of structures we observe locally. Cosmological models predict them with high confidence, yet these regions lie beyond any possible observation or interaction. They're real but untestable. This does not mean science fails at the cosmic horizon. It means science must acknowledge its domain. Scientific knowledge is constrained not only by imagination or instrumentation, but by causality itself. When no signal can arrive, no experiment can be performed. Cosmology already operates near this boundary. The early universe is inferred from faint background radiation and large-scale structure. Dark matter and dark energy are known through their effects, not their direct detection. In these cases, indirect evidence remains available. Models can be refined. Predictions can be checked. Beyond the horizon, even indirect evidence disappears. No future observation can confirm or refute what lies there. Theories about those regions are extensions of known physics, not conclusions drawn from data. They are reasonable, consistent, and mathematically sound, but they cannot be verified. This creates a subtle shift in how cosmological statements should be interpreted. Claims about the universe beyond the observable region are not discoveries in the usual sense. They are extrapolations. They describe what should exist if the laws we know apply universally, but they cannot be elevated to empirical facts. Science does not collapse at this edge. It becomes careful. This boundary also highlights something important about scientific humility. The universe does not owe us accessibility. Reality is not obligated to be fully knowable. The success of science within its domain does not imply unlimited reach. In this sense, the cosmic horizon is not a failure of inquiry. It is a feature of the universe that inquiry must respect. Paradoxically, acknowledging this limit strengthens science. It clarifies which questions are answerable and which are not. It separates speculation from inference. It prevents the erosion of meaning that occurs when everything is treated as equally testable. The universe, vast as it is, contains regions forever beyond confirmation. Science can describe the structure of those regions only by understanding the rules that govern the parts we can observe. At the edge of the knowable, science does not stop. It changes posture. And once that posture is adopted, attention naturally returns to the one region where observation, understanding, and existence overlap completely, the place we actually inhabit. That shift in focus brings the story back home, to what it means to live inside one small galaxy surrounded by a universe we can never fully reach. When the limits of reach and knowledge are fully acknowledged, the vastness of the universe takes on a different character. The universe is not something we stand outside of surveying in its entirety. We experience it from within a single gravitationally bound system. Everything we have ever observed in detail, every star, every planet, every signal, comes from within one small region of an incomprehensibly larger whole. Our galaxy is not just a location, it is the boundary of our direct experience. This does not diminish the significance of what lies beyond it. Trillions of galaxies exist outside the Milky Way. Many are visible now. Many more exist beyond the observable horizon. They shape the overall structure of the universe, influence its expansion, and carry histories that parallel our own in ways we can only infer, but none of them will ever become part of our lived reality. The Milky Way is the only galaxy we will ever touch, the only one we will ever explore from the inside, the only one whose stars we can visit, whose planets we can examine directly, whose environment we can change. This realization carries an unexpected implication. Our cosmic insignificance does not come from being small in number. It comes from being isolated in access. We are not rare because the universe lacks structure. We are rare because we occupy a particular causal island within it. Every civilization, wherever it arises, faces the same condition. Each is confined to its own galaxy or local group. Each can infer the existence of others but never confirm them directly. Each must build its understanding of the universe using the information available within its horizon. In this sense, the universe is filled with observers who will never meet. That does not make the universe empty. It makes it partitioned. Living inside one galaxy means living with both abundance and constraint. We are surrounded by more cosmic structure than we can ever interact with, yet fully embedded within the part we can understand. This creates a delicate balance between humility and responsibility. humility because we are not central, responsibility because our local region is the only one we will ever affect. The Milky Way is not just where we live, it is the entirety of our future influence. And recognizing that influence requires one final perspective, a perspective that turns the cosmic horizon from a barrier into a context. The cosmic horizon does not imprison us. It defines us, it marks the boundary between what can be known and what must be inferred, between what can be reached and what must remain abstract. It is not a wall in space, but a condition of existence in an expanding universe. Other galaxies beyond reach are not failures of exploration. They are measures of scale. They remind us that reality extends far beyond any single vantage point, even as each vantage point remains complete in its own way. We live at a moment when the universe still reveals its depth. We can see other galaxies, we can trace their histories, we can map large-scale structure and measure expansion. This window will not remain open forever. In the distant future, much of this information will be lost. That makes the present extraordinary, not because we are special observers, but because we exist at a time when observation is still possible, when the universe is old enough to be structured yet young enough to remain visible. In this light, the Milky Way is not a limitation. It is an opportunity. It is the one galaxy where understanding, action, and existence intersect. The one place where the universe can become aware of itself through us. Other galaxies may be beyond reach, but they still shape our understanding of what the universe is, and that understanding, bounded, incomplete, and fragile, is the closest thing we have to touching the cosmos as a whole.